It's a new module. Remember, module 9, kinematics, you do have homework for that. Let's see, when did I make that due? April 18th, so this Sunday. If you have last minute questions on the homework and you email me on Sunday, I can't guarantee I'll get back to you in time. I have a conference I'm attending, well, over Zoom on Saturday, but because of that, all day on Saturday, I may be scrambling to get stuff ready for next week on Sunday, because I still have to put together a test for you guys on this material. Obviously, we have some time, but yeah, so the homework is due on Sunday evening. So my response is going to be a little slow this weekend. I know some of you have sent me emails in the past and I've responded pretty quick, but for 5 or 6 hours on Saturday, I'm going to be in a conference. I will not be responding to emails very quickly at all. So just so you're aware. So that's module 9. If you go to module 10, so module 9 is rectilinear motion. So motion in rectangular coordinates. What we're going to talk about now is, we're still doing kinematics, right? So motion, we're going to talk about angular motion. So things like rotational motion. And I've also got, I got the PowerPoints here. I've got a handout as usual, broken up in either there's a single page or multiple pages with room to write your answers. All right, let's start kinematics. I'm recording, right? Yes. Chapter 11. This is chapter 11 in your textbook. We're going to look at these kinematic equations in the context of angular displacement, angular velocity, and angular acceleration. So we just talked about displacement, velocity, and acceleration in sort of rectangular coordinates, right? X and Y. Now we're talking about angular, right? So think of a, well, there'll be a graphic of this, but think of something spinning like a record. Well, record. Do you guys even use records anymore? I don't even know. Like a tire, right? Or a bicycle tire, right? It's spinning around a center, central point of rotation. Angular acceleration. Oh, so then we'll talk about angular acceleration. There's two components of acceleration: tangential and normal, and we'll get into that. Remember, acceleration is a vector, so it can have components. All right. So we talked about, well, just in general with kinematics, you can have these basic categories: rectilinear motion, right? So you're looking at a particle as it moves along a straight line, right? Position, velocity, acceleration. You've got curvilinear motion, which is if you have a particle, so let's say this is straight line. Curvilinear is going to be a particle moving on a curved line or a circle, right? It doesn't have to be a circle, but it has to be a curved, so a curved line. And then general motion, a particle follows a path that's neither straight nor circular, or one that has both simultaneously, right? So this is the specifically for a curved line of a circle, and this is general plane motion. So this would be kind of what my cursor is doing, right, around the page. General plane motion. Let's start with fundamentals here. Displacement. Okay. Angular displacement. What we typically do here is we look at the angle with which an object turns, right? And displacement's measured in some kind of angular units like degrees or revolutions or radians. So for example, you can see this fly on a record player, right? Its displacement is, you could say 90 degrees, right? Or you can, well, or you can say it's a quarter of a revolution, right? Or you can say it's, let's see, pi radians is gonna be half, so this would be 1/2 pi radians, right? And the key conversion factor here is 1 revolution, right? 1 revolution all the way around. If the fly starts here and winds up here, it's 360 degrees or 2 pi radians. Here's the units on angular velocity. Notice it's delta theta over delta t. So radians per second, revolutions per minute, those are the common common units that are given for angular velocity. And you have to be able to convert between those. And we'll do some conversions. In fact, the first example is a conversion. So, oh, omega. This is this funny looking curve W. This is an omega. It's a lowercase omega. Average angular velocity, right? Delta theta, angular displacement, which we just discussed, and obviously delta t is the change in time. Remember, these are 2 minus 1. So position 2 minus position, or angle 2 minus angle 1, time 2 minus time 1. Angular acceleration. So angular acceleration is just very similar, again, to the idea of velocity is analogous to angular. Well, let's see. Well, this is angular velocity is analogous to linear velocity, right? Angular acceleration is analogous to linear acceleration, and it's the change in angular velocity over the change in time, right? So angular velocity 2 minus 1 divided by time 2 minus 1. And the units on this are typically radians per second squared. The point about units here, you may be given information in revolutions or degrees or radians, but you don't do the calculations with revolutions or degrees. You always do these calculations with radians. And we had a taste of that with the friction, you know, the frictional, the belt friction, where you had like some kind of rope wrapped around a, you know, central cylindrical, and you're looking at, you know, how many degrees, right? What portion of that? And that was in radians. So all our calculations are going to be in radians. So you have to convert. If you're given information in revolutions per minute or rate or degrees per second, or even just degrees, you got to just convert to radians. All right. Oh, excuse me. So let's do some example conversions here. I'm going to switch over to the document camera, which is apparently frozen. There it is. Okay, so 10 revolutions to radians. This is the basic one, right? We've got 10 revolutions. We want to get radians, and we want to eliminate revolutions. So all we're doing here is multiplying by some conversion factor, right? The conversion factor is 1 revolution is 2 pi radians, right? I'll just write it in here. Or 2 pi radians is 1 revolution. So obviously the revolutions cancel. You wind up with 62.83 radians. Or you can say 10 revs is 62.8 radians. You can put rads next to it, or yeah, but rads is a unit of radiation measurement as well. So. Right, this is just 20 pi radians. Simple problem. All right. This is, we want to convert 1236 degrees to revolutions and radians, right? 1236 degrees, that's quite a lot of degrees, right? I mean, we all know a circle is 360 degrees. So if something's gone through 1236 degrees, we know it's gone through more than one revolution, right? We just put on a side here. 1 rev is equal to 360 degrees, right? Which is also 2 pi radians. So part A, revolutions. We've got 1236 degrees. And we want revolutions. And we have degrees. Degrees cancel. You wind up here, there's 1236 divided by 360, 3.43 revs. Part B, radians. 1236 degrees. We want radians. We're going to do the same thing we did up there, except here we know that 2 pi radians is 1 revolution, or it's 360 degrees, right? So we're going to use these two. 2 pi radians is 360 degrees. The radians go on top because that's what we want. And we want to cancel out the degrees. So here we get 21.6 radians. The other thing sometimes people do, and just to show it, 360 degrees is 2 pi radians, but also 180 degrees is pi radians. So particularly if you're not working with revolutions, a lot of people just like to use this because they just eliminate the 2 factor, right? It's like, well, why am I going to have the 2 factor in there? We've got pi radians is 180 degrees, right? Remember, this fraction here this is telling us the top and the bottom are equivalent to each other, right? And in terms of equivalency, pi radians is equivalent to 180 degrees. So you get the same answer, obviously. Put a little or. All right, RPMs. This is where people start getting a little messed up. They'll just forget some kind of conversion factor, conversion piece. 45 RPMs, right? We've got 45 revolutions per minute. Right? What do we want? We want radians and we want seconds, right? So just keep in mind here, right? One rev is 2 pi radians, right? But also 1 minute is equal to 60 seconds, right? We have minutes here, and we got to go to seconds. So we need that conversion factor. And we can do this all in one shot. Let me show you here. I'm going to take 45 revs per minute. I'm going to multiply by 2 pi radians per 1 revolution. This is taking care of the revs. And then the minute, I got to get rid of the minute. So now the minute is on the bottom here. I want seconds on the bottom. This tends to confuse people. We want to cancel out. You can't cancel out on the bottom. If you put minutes on the bottom, it's going to become minutes squared. So you got to cancel out on the top. So we're going to divide minutes by minutes. So we're just doing algebra with units, basically, is all we're doing. And this is 60 seconds. So what happens here? the revolutions here are divided by the revolutions here. The minutes here are divided by the minutes here. We wind up with 45 times 2 pi divided by 60. And this gets you 4.71 radians per second. Yep, 4.71. Does anyone have a question about this one here? All right, I'm expecting to see this done correctly. RPMs, revolutions per minute, you need to account for the fact that you not only have to go to radians, but you also have to convert to seconds. All right, this is nice. A gear rotates 148 degrees in 1.75 seconds. Determine its angular velocity in radians per second. So this is using look at the angular velocity here. Oops. Oh no, that's the right. What's its angular displacement divided by the time? And we're given that information, right? We're given the 148 degrees and we're given the 1.75 seconds. So I should, let me write this down on the paper because I don't have it written down. I want to write the formula the way you have it in the notes. I just wrote it over here. Angular velocity, delta theta divided by delta t, right? And delta theta is 148 degrees, but we have to work in radians. So first we're going to convert degrees to radians, right? 148 degrees. Again, we can use the pi radians over the 180. And it looks like I didn't write this intermediate step down. 148 divided by 180. Oh, times pi. Forgot to multiply by pi. We've got 2.583 radians. 148 degrees is 2.583 radians. That's how many, that's the theta, right? That's our delta theta. So angular velocity is going to be 2.583 radians, and that's accomplished in 1.75 seconds. So this is, oh, what did I have? 1.476, 1.476. So omega is 1.4, I'll round up to 8. Notice the units on here, radians per second. That's angular velocity in radians per second. I mean, you could have taken the 148 divided by this at 1.7 times this ratio, but I just wanted to show, right? You can do it stepwise. You can do it all in one shot with a, continuous set of conversions. What's my next one here? Acceleration. Yeah, I'm gonna have to do the equations for this one. All right, let's go back to the PowerPoint. All right. when we were doing rectilinear motion, we talked about uniform acceleration, right? So this is where acceleration is constant. Oh, you know what? No, we're gonna do that one. I'll do this example with the next set. Anyway, acceleration is constant, right? So sort of like gravitational acceleration is always constant. In this case, angular acceleration is constant. So we're going to work with that fundamental understanding. So it's very similar to rectilinear motion, and because the assumption is angular acceleration is constant, right, or uniform, we can write the equations out just like we did for rectilinear equations. So here's the rectilinear form on the left, and then here's the angular form on the right. Let's look at each one. We've got displacement in linear is s, and over here it's theta, right? Because we're going around in a circle. So our displacement here is number of degrees, number of rotations, whatever, radians. V naught and t, obviously time is the same. Time doesn't matter. There's no angular component of time. But the velocity, initial velocity is now initial angular velocity, right? And acceleration, notice instead of an A, they use an alpha. This is angular acceleration. This is radians per second squared. Obviously, omega is in radians per second. And you can see the analogs between them, right? Final velocity, final angular velocity. Initial velocity, initial angular velocity. So same basic sets of equations. Oh, looks like I put the reference in. This is where it is in your textbook. These set of equations. In fact, I think your table has both sets in it. But we can use these equations to solve problems in a rotational frame of reference, just like we did with these equations to solve problems in an XY, rectangular frame of reference. So there's with the name, right? Rectilinear, curvilinear, or angular. Yes, in order to use these equations, you must have constant or uniform angular acceleration. So you might hear something is uniformly accelerated, right? Or a rotating object is brought to rest uniformly, right? Uniform acceleration. This is the same question as before, except in angular. If the angular velocity is constant, then angular acceleration must be 0. Why is that? Well, because alpha is omega final minus omega initial divided by time, right? If this is constant, angular acceleration is going to be 0, right? Angular velocity does not change, so angular acceleration is 0. Oh, choose a direction. This is where you get a bit of confusion here. Counterclockwise is typically considered to be positive, right? So it's one thing in XY coordinates. Okay, X is typically positive to the right. Y is typically positive going up, right? Vertically on the page or horizontally to the right. Those are the positive directions in XY. However, in angular problems, we don't have an XY, we have a rotation about a point, right? So this is just the convention that's used. Just like X is positive to the right, Y is positive up, counterclockwise is considered positive, right? So counterclockwise rotation, counterclockwise acceleration, that's positive. Oh yeah, this is just converting. If you want to convert between rectilinear values, right, and angular values, these are the equations you use. So for example, the distance s. right? It's just r times theta. Think about this. Let me see. Oh, yeah, it's on this. No, it's not. You know what I'm going to do here? I'm going to copy and paste one of these circles. Put it over here. And I'm going to delete this. All right, there's a circle. All that work for just a blank circle. I want you to think about this first equation. The radius times theta. Theta is in radians, right? Gives you the distance. Now, if this is a wheel of a bicycle, right? And this wheel rotates one time around. Let me make a little, I'll put a little dot here. So see this little orange dot? It starts here. It makes one revolution along the ground, right? And it ends with the dot back on the ground. So it's revolved one time. It's gone through 2 pi radians of rotation, right? The distance is r times 2 pi. Think about that equation. The circumference of a circle is pi times diameter. What is the diameter? The diameter is 2 times r, right? So this displacement is basically telling you this is the amount of the perimeter that you've traveled, right? R times the angle theta. Similarly, I have some diagrams in the next 2 pages for V equals R omega and A is R alpha, right? This is velocity is equal to R times angular velocity, right? Acceleration is R times angular acceleration. Let's look at this. Oh, wait, I thought I had a velocity one. Let me just talk about the velocity real quick. If this is spinning around like a record, right, or a tire, the velocity at a given point, right, is lower on the inside. The angular velocity is the same everywhere, right? This is spinning at a certain number of radians per second, right? Like a record player or a constant velocity bicycle tire, right? But in the middle, the velocity on a little point in the middle is lower than the velocity out here, right? This has to cover, a point out here has to cover more distance, right? In that same amount of time as it rotates through that, say, 45 degrees. So you're going to have a higher velocity on the outside than you are on the inside. So that's what's kind of funny about this whole angular relationship. The velocity is different, but the angular velocity is the same anywhere on along the radius. And then the same thing goes for angular acceleration. Angular acceleration, let's talk about acceleration. Acceleration has 2 components in angular coordinates. It's got what's called the tangential acceleration, and it's labeled here A of t. And this is the change in the magnitude of the velocity over time, right? And then it's got the normal acceleration. And this is this is due to the change in these are backwards. Let's see, change in magnitude. Yeah, these are tangential is change in direction. Normal is change in magnitude. Anyway, the acceleration here can be written as a combination of these two. There's some acceleration component between these 2 vectors. The acceleration is just the sum of the squares. Sorry, the square of the sum of the squares. So you have your tangential acceleration, your normal acceleration. This is basically a vector triangle, right? Your resultant is in between here somewhere, and the resultant is just the square of the sum of the squares. So let's look at this thing that's spinning. If you've got this point over here, it's got an instantaneous velocity this way, right? Its acceleration is going to be directed kind of this way because it's say it's accelerating, right? It's got a normal component of acceleration, which is always pointed towards the center. And then it's got another component, tangential component of acceleration pointed outwards. So in this case, it falls between them. And over here, it falls between them. So notice acceleration is changing. The actual vector of acceleration is changing as you go around this, this circle, as you accelerate around the circle. This is I guess this is probably the most challenging concept for people to get their heads around, this acceleration in angular coordinates, just because of this. Well, there's always this normal component and this tangential component. Now, sometimes the tangential component can be 0, right? Let's look at the values. The tangential component is r times alpha. The normal component is v squared over r. Remember, v squared, well, v and omega are interchangeable by, right, v is omega r, right? So you plug that number in, you wind up with omega squared times r is the normal acceleration. So what does this tell us? This tells us that for a given geometry, given a circular motion, you're always going to have a normal component because that only depends on angular velocity. So as long as you're turning around and around, you've got an angular velocity, you have a normal component of acceleration, right? An acceleration is a change in velocity. In particular, going around a circle, right? A circle is like, think about something attached to a string, right? If I take that object attached to a string and I spin it around my head, overhead, that string is directing a force inward to keep that object on a circular path. That force is part of the normal acceleration, right? So remember, force equals ma. We're gonna get back on that in the next chapter. But force equals ma, mass times acceleration. Without an acceleration, you can't have a force. That acceleration is a normally directed acceleration towards the center, keeping that object on the path of a circle. Tangential acceleration just depends on the radius times the angular acceleration. So if this thing's moving in a constant angular velocity, there's no angular acceleration. So it's possible for tangential acceleration to be 0, but still have a normal acceleration. Obviously, right, if you do have a change in angular velocity, right, your angular acceleration will be present. It will not be 0, and you'll have a tangential acceleration as well. All right, let's do some examples. First one is we got a wheel turning through 500 revolutions while accelerating from 80 radians per second to 110 radians per second. Determine the angular acceleration and the time required. So this is an interesting problem. I have a little note here. I believe this says problem number 1113 in text. So this is going to be similar to some of the homework problems. Let's draw this out because, without drawing this out, it's hard to sort of get your mind around what's going on. We got a wheel, and it's turning through 500 revolutions while accelerating from 80 to 100 radians per second. So I'm just going to draw arbitrarily a direction here. And this is 500 revolutions. That's how many revolutions it takes. And it starts off at omega naught, right? 80 radians per second, and it ends at 110 radians per second. I'm going to use a little f here for final. So we're given a few things. Theta needs to be in radians. It's 500 revs. That's the displacement, right? Let's look at these equations real quick. All right. We want the angular acceleration and the time. Well, let's see. If I use this equation, I've got acceleration and time, two unknowns. If I use this equation, I've got, remember, I know the angular velocities. I know the initial and the final. I don't know anything about time or acceleration. Oh, but look at this equation. Here I've got angular velocity, final and initial. Let's see, final and initial. Here I've got the angular acceleration and theta, the displacement. Time is not part of this equation. So this allows me to solve for angular acceleration without having to worry about the time, because we need to solve for both of those, right? We need to solve for angular acceleration and time. So the first thing I can do here is I can use this equation, and I know what my omegas are, those were given. I need my theta, so that's what I'm going to solve for right now. Theta is 500 revolutions. We've got 2 pi revs per, sorry, this is radians. Radians per rev. I'm going to leave this right now with pi, just so I don't have to write a bunch of decimals. 1,000 pi radians. Omega naught is 80 radians per second. And omega final is 110 radians per second. So that's the information we're given. So I'm going to start with the kinematic equation. Omega squared equals, so this is the final omega squared. Initial omega squared plus 2 alpha theta, right? And we want to solve for alpha. Alpha is just going to be omega f squared minus omega naught squared. Final squared minus initial squared divided by 2 theta. So that's just algebra. Let's put the numbers in. We've got 110. I'm going to leave the units out in here. The units are radians per second squared, right? Omega f squared minus omega naught squared. The total units on top are radians per second squared divided by 2 times 1,000 pi radians. On top, we get a 5,700. This is radians squared per second squared. And the bottom, we get 2,000 pi radians. One of the radians cancels. You wind up with alpha is equal to 0.907 radians per second squared. That's a pi, 2000 pi. I just waited till the end just because, you know, the pi is going to give me a bunch of different decimal places. This is the angular acceleration. Now the time required, well, that's a different scenario, right? Find t. Well, let's go back to our equations. We know the angular acceleration, right? We could use either of these two. This is a much simpler equation. In fact, this comes from the definition of angular acceleration, right? Omega f minus omega naught divided by time. So we're just going to use this. We're going to solve for time. Oh, you know what? I should have written it down. Plus alpha t. We got omega final minus omega initial over alpha. 110 minus 80. We found the angular acceleration up here, 0.907. The units on this are obviously radians per second. So we were given those. And what we find here, this is 33.1 seconds. So these equations let us solve this problem, right? A wheel turns total of 500 revolutions while accelerating from 80 to 110 radians per second. What's the angular acceleration and what's the time required, right? It's accelerating at 0.907 radians per second, and it took 33.1 seconds to do that, right? That's the time it's taken to do that acceleration. Let's see, do I have time for one more? I do. Maybe. Let me close this. This is just distracting me. All right. Number 6, let's read it up here. When a gear rotates 20 revolutions, it achieves an angular velocity of 30 radians per second starting from rest. Determine its constant acceleration and the time required. So here we're going to use the same set of equations. We just have a slightly different problem to solve in terms of how it's worded, right? So a gear rotates 20 revolutions. It achieves an angular velocity. So let's first put the displacement down. Theta is 20 revs, which is what? 2 pi radians per 1 rev. This gives us 40 pi radians, just so I don't have to, again, deal with a lot of crazy decimal numbers. Starting from rest, right? This is telling us omega naught is equal to 0, right? Starts at rest just means it has no initial, velocity, angular or otherwise. And it's achieving, I'm just going to stick with the omega, 30 radians per second. Because the formulas don't actually use the subscript f. So I don't know what's going to be more confusing. So if I start with omega squared equals omega, I'm starting with the same equation. And I solve for alpha. Remember, this is 0. starts at rest. So alpha is just going to be omega squared divided by 2 theta. My theta was 40 pi radians. Oh, I got to square this. 900 over 2 times 40 times pi. You can do the math here. Alpha is equal to 3.58 radians per second squared. So notice this is a slightly easier problem because you only have to worry about one of the angular velocities, right? And then the time required. Well, the same thing, right? Time is going to be equal to, and you can see where this equation comes from. We're using this equation, final minus initial divided by acceleration, right? I'll leave the notation that the text uses. This is going to be, again, 30, this is 0. 30 radians per second divided by the acceleration of 3.58 radians per second squared. Time here is, looks like I made a 3.58, whoops, 8.3, okay, I couldn't read my writing well. 8.38 seconds. So that's how you use these equations. Yeah, I could start the next one, but I don't know. The next one's not that long, but I'd rather just pick up here on Monday. Oh, you know what? This is. Oh, yeah, this is actually fairly easy. I don't know why this is in that order. Yeah, we'll just stop here. I'll pick up on Monday with example 7. It'll be a nice, easy example to ease us into the rest of the material. Are there any questions?